Hi, I'm Ben-Yaakov. This presentation is about RM calculations in power electronics made easy. The objective here is really to lay the foundation for easy RMS calculation of PWM pulses. I'll talk about basic concept of RMS, waveform of PWM, triangular waveform which are found in many PWM systems, and then the back of the envelope calculations. Let me start off with very basic relationship. Power, if we have an impedance, we have a current, there's a voltage developing, the power will be the average of V times I dt over the period that I'm averaging it. That is, if you have the current, you have the voltage, and the overlap here will generate power or cause power loss or power dissipation in this element. Now, let's talk about a current that is flowing through a resistor, developing a voltage VR. Now, VR will be IR times R. The power will be, again, the product of V times R averaged, and therefore the power, when I'll insert instead of VR the value here, I'll find that the power will be R average of IR squared dt. This is a power-related I square expression, and the square root of this is defined as the RMS. So RMS current is a sort of power unit. When you square it and multiply it by R, you get a power. This expression or this value of this RMS is independent of the waveform. For any waveform, you can find this RMS value, which is very easy then to do the calculation. Let me talk about some basic rules here. This is again the RMS. This is the summation of RMS currents of, very important, different frequency. This is incorrect if the frequencies, or maybe incorrect if the frequencies are the same. So if you have RMS current of different frequencies, the total RMS will be the sum of these RMS squared. Now the reason that you square them, because you are summing up power, and therefore you have to take the RMS square, sum all of them, and then for the RMS you take the square root. Same thing goes for VRMS. I'm not going to talk about it too much. Now, as we talk about frequencies, let me just mention that DC is actually a frequency of 0, and as we'll see, we'll use it, and it is a different frequency from other frequencies that we'll find. Let's take a very simple example. Suppose we have a pulses, square wave pulses. The first thing I'm going to do, I'm going to sort of squeeze these pulses together, take out this gap. So I'm going to have here a constant current. For a constant current, the RMS is the value of the current. So the power for the no gap situation is the peak current, or this current here, squared times R. Defining the duty cycle as T on over Ts. Ts is the period, T on is the pulse time. We find that the average will be then P on, this is the value we have found, times T on over Ts, or P on D on. This will be the average power after we take into account D. Remember, we're doing these averaging or summation always in power units. So once replacing P on with this value, here is what I'm getting, R times I m peak square times D on. This is now actually I RMS square. This is I RMS square. So therefore the RMS is this peak value square root of D on. Let me move now to a triangular current, triangular wave shape, which is found in many PWM cases. And let's talk about this first triangle here, okay? I'm going to express this line of current rise as a function of time. So by the definition of the RMS, I'm taking the average of this value of the current. I'm sorry, T should also be squared because I have to square the whole thing, the whole current. So this is squared. And then when you take the integral, this is why it's T to the third. And as it happens, this is the value which I'm getting. So the RMS value of a triangle waveform is I peak over square root of 3. Well, it's sort of similar to a sinusoidal wave, which is I peak over square root of 2. Maybe because it is a triangular, this is 3. Well, anyhow, it's I peak over square root of 3. Very easy to remember. So once I have the RMS, of course, the power will be this RMS squared times R. Now, we've talked about this triangle, but this triangle is the same as this one, has the same RMS value. Also these, because RMS is related to power, and power is I squared, so it doesn't matter whether it's positive or negative. So the whole waveform, also the RMS of the complete waveform, is also I peak over square root of 3. Now let's take a little bit more complex situation to see how we use this results we've seen before. Suppose I have a train of waveform of this shape, which is very typical of a PWM converter, like a current of the switcher. And the first thing I'm going to do again is to close this gap, so I'll get a continuous waveform. I know how to deal with this gap. This is just square root of D. So here it is. We have this waveform now, which is continuous. Now I'm going to decompose this waveform into a DC part. This is here at the middle of this triangle. This is the DC part. And the AC part, this is the AC part. Here is the AC part. These are of different frequencies. This is frequency 0. These are, of course, if you look at the Fourier decomposition, there are many frequencies, but they don't include 0. You should not decompose it this way because this triangle has DC component, and since we are going to add these two, as we have seen before, you can add them if the frequencies are different. So this is the way to decompose it. So now we have a DC part, which is the I peak over delta I divided by 2. The delta I is the whole jump here. And this is the average value, which is also the RMS, because for a DC, the RMS is the same value. Now for the triangle here, we already know it's the peak value. Peak value here is delta I over 2 divided by square root of 3, and therefore the IRMS square is this value square plus this value square. So here it is. We have the RMS square, and when I then add or multiply it by d on in order to take into account the fact that there is a gap here, there is a t off time, and the RMS will then be the square root of this value, which comes to be the square root of d on, square root of this expression. Now this expression here is actually delta I squared divided by 4 times 3, which is 12. So this is another way to express it. You can also express it in this way. Very easy actually to remember this, but if you don't, then it's very easy also to get this expression figured out very easily. And of course the power will be this RMS times R. Let me just give another example, just for the sake of illustration. Suppose we have a triangular wave here. This is supposed to be of the same height. and there is of course a gap here, the T off, this is T on, this is the T. We know that the RMS value of this waveform is of course the I peak square root of 3 times square root of d. This is from what we have seen before. But I'm going to calculate it in a different way, just for the sake of illustration. I'm going to decompose it into the DC part. The value of the DC, of course, is I peak divided by 2, because the average is here somewhere in between. I'm talking about the average after closing the gap and sort of having a waveform which is sort of continuous, no T off in between. And the same thing I'm going to do for the triangular wave, squeezed together. And of course, if this is I peak, this value will be I peak over 2. So the RMS of this value is I peak over 2, because this is DC and this is I peak over 2. The RMS of this is I peak divided by 2, this is the height of this triangle, divided by square root of 3. And the RMS will be the square root of this value squared, plus this value squared, here it is, and which comes to be I peak over square root of 3 times square root of d, which is of course the exact value that we have found before. This is just to illustrate how we can decompose waveform to get the RMS value. This is all what I wanted to show you in this clip. Thank you very much for your attention. I hope it is of interest and perhaps you can use it in the future. Thank you.